Welcome everybody to another video. This week, there's been a huge announcement of the Nobel Prize for Chemistry. We're going to actually check out the structures, take a look at them in VR. So it's going to be a fun time.
Yeah, thanks, Kata. Yeah, new Nobel Prize in Chemistry just dropped. So, of course, we have three Nobel Prize winners for that. One of them is Susumu Kitagawa out of Kyoto, and I'll be mostly highlighting work from him, but also, mention Richard Robson from Australia and Omar Yaghi, from UC Berkeley. So, really awesome group of people that have been publishing a ton of papers on metal organic framework synthesis, design, frameworks while you're designing them. Sorry, excuse the pun, but things to think about spatially when you're designing these. And I've got some really great information taken from Professor Kitagawa's website, and he is really bullish on MOFs. I'd say is probably the main takeaway from reading through everything that he had on his website, right? So he completes his PhD in University of Kyoto in 1979, and then just gets really into the supramolecular chemistry and porous polymers.
Before we dive in, actually, if you could give a little bit of an overview of MOFs for those of us who might not be familiar as much. And, I know we typically cover more on the organic side of things, and, biology and kind of biochemistry side of things. So if you could kind of give that overview.
Yeah, no, it's a good point. So metal organic framework, let's see what the best way to describe it. It's a three-dimensional structure that is made, like you design a ligand in order to coordinate the geometry with metals in order to build this big three-dimensional cage. So that's kind of like the layman's way I would describe it, but I think it goes a bit deeper than that. If you look at creating these, you could kind of think of it as like, what do you want to put inside of it? So some people are using it for like gas storage is really popular, like hydrogen and methane storage. There's a lot of work being done right there, or nitrogen, really like any gas you might want to store. You can only store so much in an empty container, and you can actually store a lot more by filling that container with the metal organic framework. So that's really
So are
cool.
these kind of I think the theoretical applications have been, filtration, I believe, is kind of the big one, right?
Yeah, so I mean, it could be water filtration, it could be heat pumps, chillers. Let's see, I collected a bunch of these from his website. Capturing and degrading toxic gases and vapors. The methane storage I mentioned. They could be catalysts. They basically, he said a really great quote, right? They provide a unique three-dimensional space for a very interesting chemistry to happen. And so, you wouldn't really have these conditions anywhere else besides right inside that MOF. And so you could create these really unique situations that influence chemistry, whether that's things that you might want to bond in certain ways, or maybe you want to hold something in place and then break it apart with something else. This is a toolkit for doing things at the nanoscale, and you could pretty much make them any size. Like it could be very large. I have some very large ones, or MOFs with very large spaces in between them to show, and then we'll also have some with very small spaces in between to show. And there's like hundreds of thousands of these available on different databases. One of them that we're going to be highlighting, where a lot of these came from, is from Northwestern University. So they have a whole MOF database that you could check out at mof.tech.northwestern.edu. And that's where I pulled most of these structures that you'll see today. Again, he's really bullish. I'm going to read this whole, I think, final paragraph that he had on his website. The time will come when MOF research will expand upon the three research fields and change the foundation upon which it was built. So the three research fields being cluster chemistry, organic chemistry, and X-ray crystallography. All those working hand in hand. Really has enabled the MOF industry, and now like MOFs are going to revolutionize all three of those. So he says, for instance, we've already witnessed clusters that cannot be made in solution, but can be stabilized in a MOF, right? So you can't make it without the MOF. The only way to have it is by having the MOF in there. We should be able to trap reactive intermediates and significantly alter the pathway reactivity and selectivity for an organic reaction. So like getting really specific, like basically changing the entire field of organic chemistry by incorporating MOFs in the synthesis, because you could just make that so selective because you could control every component down to the angstrom and the nanoscale. Then he goes on to say we could use a MOF as a matrix for crystal structure determination for macromolecules such as proteins. Like, that's cool. Like, so there's so many things. Yeah, we've only scratched the surface in MOF research. So again, like he's really bullish. He thinks that MOFs still have a long way to go. So even though Nobel Prize was just awarded for it, it doesn't mean it's a very mature field. All things considered, there's not really too many people in the world that are doing this type of research, but it's really amazing, and really like any organic chemist wanting to get into this field, they spend apparently 80% of their time performing organic synthesis. So if you're an organic chemist in another industry and you want to get into MOFs, there's a ton of overlap, and I'm sure that there's a lot of companies that are more interested in doing MOF research now that it's gotten a Nobel Prize.
Awesome. Super exciting. So I guess let's jump into VR and check out these MOFs.
So I've loaded a few meta-organic framework structures from that Northwestern University database. So you can see here that we have some very cool symmetry, as is very common with MOFs. And it looks like one of the best ways to design MOFs is actually spatially. And it seems like there's a few packages. One of them is called Tobacco, that allows you to basically using geometry come up with new MOFs. So if you have specific shapes or sizes, you could fine-tune the MOFs to help be various shapes, various sizes, depending on what you're trying to put inside of it. This one in particular, I think, has a very large space in the middle. You can imagine that a large molecule or a small protein or something like that might be able to fit inside of this one, versus others you could barely fit a few atoms in there. So we have loaded 4 structures into Nanome V2. I used Mara to help set up some of these workspaces just through the online web companion app. So that was really fun, just drag and dropping, importing them through the web app. Of course, I did some file cleanup using both Nanome V1 as well as Vesta from JP Minerals. So it's always nice to use those tools for dealing with .cif structures. Unfortunately, the supercells that I made, this is just one cell right here. The ones where I have many of these side by side, were just kind of a lot of atoms. So it didn't look too nice compared to just having a single cell of this. But even with a single cell, you could see that they're really some beautifully symmetric structures. And you can imagine that if you make changes with this threefold symmetry ligand right here, and of course you have this metals where they're all kind of coordinating together. If you change these ligands, then you could change the geometry of the entire structure. So instead of looking at it as how do you design a new ligand to fit in a protein, it's how do you design these molecules to all fit together to create some larger shape. And that's pretty much the concept of meta-organic frameworks, is this 3D molecular building. So I think they're beautiful. I think they're awesome. I love MOFs. I think the Nobel Prize is actually very well deserved. So we're going to add some representations. So we have our stick view, and let's go ahead and make that into van der Waals. So you can see with the van der Waals view, it's pretty much just a little cage. You can imagine that there's a lot of things that could go through this or fit in here, maybe get stuck, get held there. I'm not sure what exactly this one in particular was for. Also, these coordination sites are pretty cool to look at. But each one could have a fine-tuned application, and there's already hundreds of thousands of these available on databases, and of course many orders of magnitude more that haven't ever been discovered yet. So yeah, we're just scratching the surface on MOFs and everything that they can do. Okay, so I've loaded this other MOF actually inside the one that we just had. So you can see the yellow carbons is the one that we were just loading, and this new one is actually a little bit smaller. So I'm gonna just hide the first one, and you can see this other MOF has a similar sort of threefold symmetry, but it's much smaller. So the other one kind of had these longer arms there, and so these ones have much shorter arms, and so that makes the entire cavity much smaller. And I think this is actually a great time to use a measurement tool. So if we were to just measure from, let's just say, right there to the other side of this, and we'll go right there. That's 35 angstroms across, so 3.5 nanometers in that direction. And if we take the original one again, and we show that, you can see that it's much larger. And if we make some measurements, so let's go from there to, we'll just do the other side right there. That's about 58 angstroms. And so again, the whole point is that you could tune them to be however big or small you want them to be. So if you want it to be, 58 angstroms and not 60 angstroms, right? You could do that. If you want it to be 35 angstroms and not 33 angstroms, you could do that. These are infinitely tunable, basically. Well, not quite infinite, but in terms of practicality of chemical space, it might as well be, because we're never going to brute force our way through all of them. It's a cool view. Yeah, and just saying the symmetry there. So also, I guess we could kind of align the symmetry of the two molecules. Yeah, I mean, they're both threefold symmetry, but they don't have to be. Yeah, and then the other thing is the nesting of these. Yeah, I think I have seen some people that are trying to do kind of what we've done here, which is to have these Russian nesting doll type of inorganic frameworks. I do think it's a bit harder with the chemistry of everything, but yeah, I'm not saying these two will necessarily go together, but they do fit into each other quite nicely, even with van der Waals. So that's pretty cool. So yeah, with this one, it's a bit different. You can see that this one has more of a fourfold symmetry. Not quite. I think that's technically more of like a twofold. But anyways, it's got 4 things coming out of it. That are all pretty much the same. You have this triple bonded carbon connected to a benzene ring, another benzene ring, and then another triple bonded carbon ending over here with these oxygens. So that gets coordinated around a chromium. So yeah, they got 3 chromiums and an oxygen in between 1, 2, 3, 4, 5, 6 of these little ends. And those all come together to form this kind of cool shape that maybe is more going in this long axis. But if we take the measurement across, let's see that 15 angstrom kind of shows a little triangle in here as well. Oh, interesting that they're all 3 slightly different. They're all around 16 angstrom, but 1592, 1604, 1614. Yeah, you get things like this with how things are slightly bent in different ways. I'm sure there's some flexibility with this big pocket. But with this, you can imagine that there's maybe something sitting inside of this, and now something else comes along and binds with it or catalyzes with it. Just being able to control the geometry so precisely is so awesome. Let's put a van der Waals on this as well. Show that view. Cool. So you can just imagine, like billions of these things all around, creating this big, 3-dimensional network where things could, go in between these channels. So this one is a bit different. If we look at, maybe one of the individual ligands here, you can see how they're all pretty much the same, and then they coordinate together. And then the spaces in between these, when we do the van der Waals view, it's going to be much smaller. So you'll see that, you know, maybe these spaces in between could, you know, kind of fit maybe a hydrogen or a methane, maybe in there. But these are basically very small spaces in between here. You kind of get an idea of the 3D lattice. And yeah, in terms of measurements, I guess there's a couple ways that we could do measurements, but maybe just one would be to do it from, you know, here. Yeah, so this is like kind of the shape, but you also, you know, if you look inside, a lot of this space of, you know, 12 by 12 by 12, this is filled as well. So it's not like there's a completely empty 12.76 angstrom space. You know, but there are, you know, even smaller bits. So maybe if we could zoom in and kind of get into these little pores, you know, what are the small spaces in between? What is that? 5.59 angstrom. So, you know, half nanometer, very small spaces for molecules to go. So I'm guessing this one might be more of like a gas storage type of one. But yeah, I wanted to show the breadth of MOFs that you could have, you know, really small spaces in between and really large spaces in between. And it all depends on how you choose to design them.